Hello class, this is lesson 5-4, which is all about how to use medians and altitudes. So two different things. So first let's just talk about what is a median of a triangle. Okay, what it is a segment from a vertex to the midpoint of the opposite side. Right? That's what a median is. So we're thinking of a segment, okay? And it's starting at the vertex. So if I start right here, and if I draw a line to the median of the other side, or to the midpoint of the other side, that is a median right there, that segment. How about if I start right here at this vertex, and I go to the midpoint of the other side, that segment is another median. And I'm going to start at this vertex and go to the midpoint down at the bottom, and that one right there is also a median. Okay, so there's just a little diagram, and as you can see, all three medians of a triangle are concurrent, and they meet at one point, and that point is called the centroid. Okay, so this point right here is the centroid, where three medians meet. We're going to learn later what it means when three altitudes meet, so don't get those confused. So our first theorem is based on medians, and it's called Theorem 5.8, the concurrency of medians of a triangle. And so let's read what it says. It says that the medians of a triangle intersect at a point that is 2/3 the distance from each vertex to the midpoint of the opposite side. So it's saying that if I have this median right here, AE, well, the distance from A to that middle point where they intersect is 2/3 of the whole length A to E. Pretty cool that they found out that this fact is true in all cases. So we're going to write down the medians of triangle ABC meet at point P. Okay, this would be called the centroid. And because of that, AP, the length from A to P, is actually 2/3 of the whole length across A to E. And also BP is 2/3 from B to F all the way across, and also CP is 2/3 of the length from C all the way to D. So pretty cool theorem. I like it a lot. So let's do an example that's using this information. In triangle HJK, P is the centroid, so we know that middle point, and because it's a centroid, that's telling me that all of those segments that you see are actually the medians of this triangle. And we're also given one length from J to P that it is 12, so that's already labeled in our triangle. It wants us to find PT, and it also wants us to find the whole length from J to T. So I know, based on that theorem, that JP is 2/3 of the entire length from J to T. I can use this and work backwards. Since I'm given JP, which is 12, I'm going to plug that in. And then the way that we get rid of a fraction that's being multiplied, sorry, that should be a J, is by multiplying both sides by the reciprocal, 3/2. So those are going to cancel out, and I'll be able to find what JT is. It's going to be, looks like 18. Okay, so the entire length, JT, is 18. So if I know the whole length, JT, and I want to subtract JP, that'll help me to find out that other little section from P to T. So JT was 18, JP is 12, which means that PT must be 6. And I'm done. So you'll probably do some examples like this when we get into class, okay? That's all that we're going to talk about for medians. Pretty straightforward. So now let's look at what is an altitude of a triangle. This is probably a term that you've heard before in all of your years of math. And an altitude, if you recall, is the perpendicular segment from a vertex, right? And it's going to either the opposite side or the line that contains the opposite side. So let me show you probably the most basic one that you know of. This is where you're drawing a segment from a vertex to the opposite side, and it is creating a perpendicular line. So this blue segment right here is called the altitude of a triangle. But sometimes you're going to have a triangle where this line isn't actually going to be inside of the triangle. And that's why there's this other situation where sometimes it might start at a vertex, but it's going to have to go straight down and form a perpendicular line with the line that is including the segment of that triangle. Okay, so that's why I drew it dotted. And that would also be an altitude of this triangle, even though it's not inside of the triangle. So our next theorem has to do with altitudes. This is Theorem 5.9, and it's titled The Concurrency of Altitudes of a Triangle. So concurrency again means where all of those altitudes meet when you're given a triangle. So what it says is the lines containing the altitudes of a triangle are congruent. So it's a pretty awesome fact. So that means every single time that you draw the 3 different altitudes from the 3 different vertices in a triangle, you're going to find that they are all going to meet at one particular point. Okay. What I want to write here is that the lines containing AF and also BE and also CD meet at point G. Okay, so they're all going to meet at a specific point. And that specific point is called the orthocenter. So don't confuse it with where 3 medians meet. Okay, that's something different. So the orthocenter of a triangle is where all 3 altitudes of a triangle intersect. So let me show you something right here. This is an acute triangle, and as you can see, when I drew all 3 of the altitudes, where it's coming from a vertex going straight to the opposite side and meeting at 90 degrees, the orthocenter, P in this case, is inside the triangle. Okay. I have another interesting situation. This one is actually a right triangle. So from this vertex, it's pretty easy to go straight across and draw the altitude. But the sides are also altitudes, because if I start at this vertex to go down to the opposite side, it's already exactly the side. And same with if I start at this vertex and go to the opposite side, it's forming a right angle, 90 degrees at that side. So for point P in a right triangle where all 3 of them meet, P is on the triangle. Okay. The last instance is a little bit trickier. This is an obtuse triangle. And as you can see, because it has this very wide angle right here, we're going to be finding this P very far away from the triangle. Okay, the orthocenter is very far away, because from the bottom, if I took my ruler and drew the altitude going straight down from this vertex, I'm going to actually have to continue it going way up high, because the altitude for this vertex is not going to go in this direction. That's not going to form 90 degrees. It's going to go out. And same with the one from this other bottom one. So P is outside the triangle for every obtuse triangle that you have. So this is all that we're going to cover today. I hope that it was pretty clear and that we'll be able to get to work as soon as you come to class.